Welcome friends. Our next topic is analog pulse modulation. Analog pulse modulation is a type of continuous wave modulation. In this, parameters such as amplitude, duration or position of a pulse train varied in accordance with the message signal. So accordingly, in analog pulse modulation we have pulse amplitude modulation, pulse width modulation and pulse position modulation. Pulse width modulation is also called pulse duration modulation. So in PAM, that is called pulse amplitude modulation, the amplitude of the periodic pulse train with constant width called carrier signal is varied continuous in accordance with the message signal. Here practically we use flat top sampling process with the help of sample and hold circuit. Next, in PWM or PDM, amplitude remains constant, only the width of each pulse in a periodic pulse train varies continuously in accordance with the message signal. So here, the width of the pulse train varies according to the message signal, then the process is called pulse width modulation or pulse duration modulation. And in last, that is pulse position modulation, the amplitude and width of each pulse remains constant, only the position is changed according with the message signal. So in PAM, width and position of each pulse is fixed, only amplitude varies according to the message signal. In PWM or PDM, position and amplitude remains constant, only the width or duration changes. And in pulse position modulation or PPM, both amplitude and width remains constant, only there is a variation of position of each pulses. Now, we first talk about pulse amplitude modulation, that is called PAM. As we know that in PAM, the amplitude of continuous regular spaced pulses are varied in proportion to the corresponding sample value of message signal. PAM process is similar to the flat top sampling method. In this, the top of each pulse remains flat by using sample and hold circuit. Here, G function of T is PAM signal corresponding to the amplitude level of modulating signal MT. This PAM signal having pulse width equals to capital T and sampling period Ts. And for the generation of PAM signal, two operations are involved, that is called sample and hold operations. In these operations, we have instantaneous sampling of modulating signal and lengthening the duration of each sample or pulse. So, for instantaneous sampling of message signal, there is a criteria of sampling with sampling rate of Fs. This is called sampling frequency and it is equals to 1 upon Ts, where Ts is called sampling period, and this is according to the sampling theorem, which says that Fs is always greater or equals to twice of Fm for the recovery of the original baseband signal. And in order to avoid excess use of channel bandwidth, we can increase the duration or width of each pulse so that each pulse occupies some finite value of T. As the value of T increases, that is width, the channel bandwidth decreases, since bandwidth is inversely proportional to pulse duration capital T. So, for the generation of PAM signal, there is an involvement of instantaneous sampling as well as lengthening the duration of each sample. That is called sample and hold operation. So, in the analysis of PAM, we require sample and hold filter. Mathematically, PAM signal is expressed as G function of T equals to summation n equals to minus infinity to infinity m function of nts into h t minus n ts, where ts is called sampling period and m function of nts is the sample version of modulating signal, which is obtained by sampling process at t equals to nts. And ht is called standard rectangular pulse of unit amplitude and duration of capital T, that is shown in figure. And according to the expression of PAM signal, this standard rectangular pulse shifted equally both positive and negative time axis, and the amplitude of this standard pulse varies according to the sample value of modulating signal. So after using sample and hold filter, we get flat top PAM signal. Mathematically, PAM signal is obtained using ideal sampling. Initially, we take any arbitrary baseband signal MT and a periodic unit impulse train as function of t, and it is equals to summation n equals to minus infinity to infinity del t minus nts, where del t minus nts is time shifted delta function. And after sampling at t equals to nts, we get m del t, which is simply the multiplication of m nts and s function of t. In place of s function of t, we can write summation del t minus nts with a limit n equals to minus infinity to infinity. So the sample version of message signal, that is m del t, is equals to summation m nts into del t minus nts with limit n equals to minus infinity to infinity. Now for the generation of PAM signal, that is pulse amplitude modulation, we perform some modification. In the modification, we take a standard rectangular pulse h function of t. After taking the convolution of m del t and standard rectangular pulse ht, we get PAM signal. So convolution of m del t and ht is equals to integration m del tau h t minus tau d tau with a limit tau equals to minus infinity to infinity. In place of m del tau, we can write summation m nts into del tau minus nts. And to solve this expression, we take del tau minus nts within the integration as it has variable tau. So after this arrangement, we get convolution of m del t and ht equals to summation n equals to minus infinity to infinity m nts integration del tau minus nts h t minus tau d tau. Here tau limit is from minus infinity to infinity. Now within the integration with the variable of tau, we use shifting property of delta function, and according to this property, convolution of del t and ht is equals to ht, which means the convolution of any function with delta function is equal to the same function. So del t convolution ht is equals to integration del tau ht minus tau d tau, but in above equation we have shifted delta function, that is del tau minus nts. So the convolution of del tau minus nts and ht is equals to ht minus nts. That is called shifting property of delta function. So in place of integration term, we can write ht minus nts, and equation becomes m del t convolution ht equals to summation n equals to minus infinity to infinity m nts into ht minus nts. And what is this summation? This is PAM signal denoted by g function of t. Here PAM signal composed of shifted rectangular pulse, but the amplitude of each rectangular pulse varies according to the sample value of modulating signal.